All right, guys. So we're gonna start chapter 3 today. It's gonna be broken up into 3 parts. So 3 lectures total. And today I'll give you guys the first lecture. Um, so this is necessary for you guys to do this nomenclature worksheet. And so that's why I'm doing this live right now for you guys. So we'll go for about an hour and then you guys get the rest of the period to complete the worksheet. So chapter 3 is on molecules, compounds, and chemical compounds. I'm going to share the screen here on the Zoom. Okay, so we're really getting into, the chemistry now. You guys just learned, moles, molar mass. So now in this chapter, we're going to go into naming very first. That's what nomenclature means, so that you guys know what these compounds are that we refer to. So, you can ask the question, right? How many different substances exist? Well, just imagine how many elements there are on the periodic table, and if you combine all those, there's a huge diversity, right? There's a great amount of compounds, infinite amount of combinations. So that's not what chemistry is about. We are not to memorize every compound there are on Earth. That just would be impossible, right? But what we can do is we can classify different types of compounds so that when we meet a new compound, even though we've never seen it before, we can actually understand what it is, right? Just based on, some bonding theories. Okay. So when elements combine to form something new, they are vastly different than what they were before. Okay. So for example, if you have hydrogen, oxygen, and water, right? That's, H2O. If you combine those, you can make water. Of course, you can make other things too, right? You can make hydrogen peroxide. But water is totally different than the elements H2 and O2 going to form it. Okay, so as you can see, hydrogen and oxygen, the elements are gases, while water is a liquid, right? It's totally different. The boiling points are very different. Okay. The flammability, hydrogen is explosive. Oxygen is necessary for combustion, right, to burn things. And water is actually the opposite. You throw water on a flame, it extinguishes it, right? So the moral of the story is the compounds that form from the elements are vastly different than what you started with, okay? And that's often what we see, okay? And even the slightest differences, right, in structure can result in very different compounds. Okay. So mixtures and compounds, let's review that, right? Remember, mixtures when you have multiple components. In a mixture, elements can mix in any proportions whatsoever. However, in a compound, elements combine in a fixed definite proportions. So that's the law of definite proportions, right? So if you are water, you must be 2-to-1 hydrogen and oxygen, right? 2 hydrogen to 1 oxygen. Otherwise, you would not be water, right? Okay, so here's a picture that illustrates that, right? You have in the balloon here, the 2 original elements, right? Hydrogen and oxygen, and they're gases, right? So they look very different than when combined, you have water, just a fixed ratio of 2 hydrogens to 1 oxygen atom, right? And it's very different. State of matter is liquid versus gases here, okay? Okay, so now let's talk about chemical bonds, right? So why do elements get together to even form compounds, right? Why don't they just stay as elements? Does anybody know the answer to that? Yes. The electrons, okay, well, we elaborate more. Are elements stable? No, they're very reactive, right? Yes, and it does have to do with the electrons. If you just simply think of a hydrogen atom, how many protons does hydrogen have? Let's say this is hydrogen, right? How many protons? 1. Okay. Okay, everybody get your periodic table out, right? You have it? Same thing that you would do when you're watching my lecture, not live, right? On video, you should do the same thing. So 1, and how many electrons does hydrogen have? 1. So that's here, negative, right? Okay. Now you can have another hydrogen, okay, that has a proton and an electron as well, right? Okay. So why would these two atoms attract? Well, don't opposite charges like each other? So it's actually the proton of one attracting the electron of the other. Okay. So that's a very simple answer to the question of why elements don't stay separate. Because there is a mutual attraction, right? And so that's why these two combine to form hydrogen, the element, right? Elemental hydrogen, which is 2 hydrogen atoms, okay? H2. Okay. So that's what we are talking about when we're talking about chemical bonds, okay? Chemical bonds, right? Why things are attracted to each other. And we can classify chemical bonds into very roughly 2 categories. One is ionic, the other one's covalent. Who knows what ionic is? Yes. Very good. Yep, it's often a metal and a non-metal, but even more generally, it's a plus and a minus, right? So the metal tends to be the cation, right? We discussed that in the last lecture, right? Metals like to lose electrons, right? And non-metals like to gain. So when metals lose electrons, what charge do they become? Positive. And then when they gain electrons, they become negative. And the opposites do what? Attract. Exactly. And so that's exactly what an ionic bond is. The simplest, example that we love to give is table salt, sodium chloride. Sodium chloride is an ionic compound because sodium is a metal and it lost its electrons. So sodium is plus, okay? And Cl is negative. Exactly, okay? So when the electron goes from the sodium to the chlorine, right? They're oppositely charged now, so they attract, okay? So that's ionic. And covalent, you guys know what covalent is? They share electrons, exactly. So sharing electrons, that means you don't have a metal and a non-metal. You have all non-metals, right? So all non-metals tend to share electrons. Yeah. So those are the 2 main types, right, of bonding that we're gonna learn right now. So ionic compounds, right, because you have such great attraction between the plus and the minus, you get a very good, very tight bond, right? A very strong bond. So that's why you see ionic compounds are oftentimes they're in the solid state. Okay, they're not in liquid or gas, right? They're solid states, and they're actually in a crystal lattice. Okay, so if you have sodium chloride, what you have is a Na plus and a Cl minus, and they're just like magnets, right? But it's repeating. It's not just 1 plus and 1 minus. It's sitting right next to another plus and another minus, right? And this repeats. Okay, this repeats in 3D, 3 dimensions, right? So we can keep going here and say that's minus, plus is going to be here, right? And so on and so forth. Okay, so plus, minus, and that's what we call crystal lattice. So here's an example, right? How did table salt form? Well, everybody, look at your periodic table. Does anyone not have a periodic table with them right now? Okay, let me just pause this for a second. Stop share. All right, guys. So take a look at your periodic table there. Okay, so how does sodium chloride form? All right, where's sodium? What group is it in, everybody? What group is it? 1A. And so does it want to lose or gain electron? Lose. How many? 1. So what is its charge going to be? Positive 1. Exactly. See? So normally sodium has 11 electrons. It's going to give away 1. Now has 10 electrons. So it's positively charged. And chlorine, what group is it in? 7A. So what does it want to do? Gain an electron. And it originally had how many? 17 electrons, right? If it gains one, it becomes 18 and what charge? Negative. Exactly. And so what is the sodium plus and the Cl minus going to do? Attract each other. Exactly. And so this is what I drew, as the crystal lattice, but right, in reality, this is two-dimensional, right? It's hard to show. In reality, you see that it's 3D, right? Plus, minus, plus, minus, plus, minus. So we actually don't refer to sodium chloride as a molecule because it's not a molecule. It's not an entity, right? It's part of a much larger structure called the crystal lattice. So we call, NaCl as a formula unit, okay? That's more accurate, right? It's not a molecule, right? So all ionic compounds are that. It's not just sodium chloride. It could be, calcium chloride, lithium bromide, right? If it was lithium bromide, it's Ni plus Br minus, okay? And it would still have this arrangement of three-dimensional repeating crystal lattice. All right, so how's covalent compounds different? Well, there are no charges now, right? So ionic compounds had charges. Why? Because one thing completely lost the electron and the other thing completely gained it, right? In covalent bonds, you don't have that because you have both nonmetals, okay? So what they do is they share their electrons instead. They share their electrons to get to the noble gas, right? So remember why sodium only wanted to lose one electron? Because the closest noble gas is what? Neon, which is to the left, right? So everybody wants to be like the noble gas, right? In covalent bonding, they do that by sharing electrons, not by gaining or losing. Okay, so then you don't have charges, right? So in covalent bonds, the electrons are being shared right in between the two atoms. Okay, so this is the most stable configuration where the electrons are completely laying between the two nuclei, right? The positive and the positive are the two nuclei of the atoms that are sharing that electron. Okay, so that's why covalently bonded compounds are called molecular compounds. So they are actual molecules. Right? Okay, so when you represent compounds, you can see that the way we write it is we have subscripts to tell you how many of that atoms are in there. So you have H2O, right? H subscript to O. The 2 tells you that there are 2 hydrogens, right? And if there's just one oxygen, you don't have to write O1. Okay, it's implied, right? So that's how that works. Carbon dioxide, CO2. See, again, it's a subscript 2, and you should write it like that, right? 2. Don't write it like this, right? Don't write it like that. Write it like this, okay? So the little 2 tells you 2 oxygens. CCl4, the little 4 tells you that there are 4 chlorines, okay? Okay, let's talk about the types of chemical formulas. They can be generally categorized into 3 types: empirical, molecular, and structural. Let's go through each one of those. So the empirical formula gives you the relative number of atoms of each element in a compound, and the molecular formula gives you the actual number. Okay, so the empirical formula is like the reduced form of the molecular formula. So let's go through these examples and you'll see what I mean. So hydrogen peroxide, the stuff they use to treat wounds, has a molecular formula of H2O2, right? That's the real formula, okay? But you see that you can reduce 2, right? So think of the lowest common, denominator that you can have. So 2 can divide by 2, right? So the empirical formula is therefore HO. Exactly. So you divide by 2. For B2H6, the greatest common factor is, again, 2. So the empirical formula is BH3. Okay, right. So the empirical formula is always the simplest formula, right? Reduced from the molecular formula. Does that make sense, guys? Right. Now, for some compounds, the empirical formula can be identical to the molecular formula. So CCl4, can we reduce that down anymore? No. So CCl4's empirical formula is also CCl4, right? So that can happen. Okay. Okay. And here's a thing to notice too. If you take H2O2, what is its molar mass? Let's calculate that real quick, everybody. Let's stop share here so you guys can see the board. What is the molar mass of this one? Yep, quickly calculate it. It's gonna be like 16 times 2, right? 34.016. And what's the unit for molar mass, everybody? Grams per mole. Okay, okay. So what is the empirical formula now? HO. What is its molar mass? Very good. It's got to be half. Yep, 17.08 grams per mole. So you see that there's always a factor that separates the molecular formula from the empirical formula, right? What is that factor in this case? 2. So if you want to go from empirical formula up to molecular formula, then it's times 2, right? You want to go back down, then it's divide by 2. And it's the same here, right? With the mass, okay? So this is kind of a cool thing to realize later on when we're doing like how to get empirical formulas, how to determine molecular formula, right? Is to see how many times the smaller number goes into the bigger number, and that's how you can get the factor, okay? So that's how all these formulas are going to work, okay? Okay, so the next type of formula that we're going to talk about is the structural formula. So when you just write it like this, you don't know what's bound to what, right? So in the structural formula, it's more informative because it tells you, okay, the oxygens are attached to each other, and then the hydrogens are attached to the oxygen, right? So a structural formula is more informative. Gives you more information, right? More informative, tells you what's connected to what. So it's actually preferred if you know the structural formula, then write it. But sometimes we don't have enough information. We only know what are the atoms that are inside, right? So it's really a way to communicate how much we know. Okay? That's why we have all these different types of ways of writing formulas, which is trying to communicate, right? Communicate the most information that we know. And sometimes the most information we know is just the empirical formula, okay? And then we need to do more work to figure out what that compound is, right? Okay, you guys practice. You guys tell me, what is the empirical formula for C4H8? CH2, very good. Victor. B2H6. Who else wants to do that? Yes. That's okay. What's the biggest factor you see here? Well, if 2 divide by 6, you get a whole number? No. So what's the biggest factor here? Just reduce this down. Right? So what's the biggest factor? 2. So what's 2 divided by 2? 1. What's 6 divided by 2? So empirical formula is BH3. That's all you do, right? Okay. We did that one already. I'm gonna give you guys a better one. C8, C6H12O6. Who wants to do the empirical formula of that one? Very good. Factor is 6, right? CH2O. Very nice. Okay. All right, let's keep going. How about C5H12, guys? Empirical formula of C5H12. It's still C5H12. Yeah, can't reduce it further, right? So next one, Hg2Cl2. HgCl. And then we got C2H4O2. CH2. Oh, very good. Okay, I think you guys got it. Okay. Another way to represent molecules is through using molecular models, and we'll whip those out in another lab at one point. But molecular models shows you how these molecules look in 3D. And it's a really good learning tool and teaching tool as well. So if you guys have, about 15 bucks that you don't mind parting ways with, 15 to 20 bucks, go on Amazon and grab one of these. It's going to really help you in this class and also the future classes that you're going to do, even like biochem, a lot of science classes. This would be really helpful. So in these molecular models, they're color coded for certain atoms that are really common. They actually have color code, and everybody kind of agrees worldwide. So they see a black ball, and everybody's gonna be like, "Oh, that's a carbon," right? A white one is hydrogen, blue is nitrogen, like the sky. Oxygen is red, like blood. Fluorine is like an off-white. Phosphorus is like darker blue because it's in the same group as nitrogen, right? Sulfur is yellow. I'm thinking because of the rotten eggs has like a sulfur compound in it, right? Like the yolk of the egg. Chlorine is green, right? It does look kind of green when it's dissolved, right? So that's what we call the ball and stick molecular model, where the stick represents the bond, okay, and the balls are the atoms, okay. So here we go. This is the multiple ways in which we can represent compounds. From the left, least informative, it's just the molecular formula, right? CH4. Structural formula, more information. It's like what's connected to what. The carbon is connected to 4 hydrogens, right? And you got your ball and stick model, which shows you, okay, this is in 3-dimensional, what it should look like. And then the space filling model, the last one is informative too, but in another way. It tells you how much space each atom takes up, right? Which, normally you don't think about, right? So when it matters, you can use the space filling model to do certain things. Okay, so, in summary, these are the types of formulas that we use in chemistry, right? And there's various examples on the screen that you can see there. So at the end of the day, it's just how much information do we know and how much, we want to convey, right? Okay. All right, so this is just an overview now, just of like the atomic level view of elements and compounds. You guys have seen this before, right? Under pure substances, you can have pure elements or pure compounds. And then those subcategories, right, you can have the atomic element, which means it's just a single atom. So most elements are just a single atom. So for example, if I say iron, you guys are gonna write Fe, right? If I say cobalt, you're gonna write CO. The element is just one atom. However, there are what we call molecular elements, which means these elements comprise of 2 or more atoms. So that would be like the oxygen that we breathe. Oxygen, the element, is not just O, it's O2. Exactly. Yes, you had a question? That's right. That's what they call diatomic elements. So most of them are monatomic, meaning just one atom, right? But there are some that are diatomics, and then some are even more than diatomic. So sulfur actually comes in 8. Phosphorus comes in 4. Yeah, so you just kind of have to learn those. They're not many, okay? And then, yes, go ahead. 8, yeah, it's S8. P, naturally occurring, P4. Yeah, right. So under compounds, you have molecular and you can have ionic, right? Remember what ionic is? When you have a complete transfer of electron and you get opposite charges, right? Plus and minus that attract each other. in a crystal lattice. And then you have molecular compounds where the electrons are just being shared. There are no charges, right? And so there you can see discrete molecules, right? They're not in a crystal lattice that's plus, minus, right? They're discrete molecules that you can count. Like in this picture, you're like 3 waters, right? So that's sort of the overview, right, of how things bond together. So the only thing I want you guys to remember as far as the non-monatomic elements, it's just memorizing the diatomic. Okay, so diatomic ones are 2 atom. And I have a mnemonic device for you guys in order to memorize it. It's just Hofbrinkel. You guys see that? Hofbrinkel, because H2, O2, F2, Br2, I2, N2, and Cl2. Okay? Hofbrinkel. So you need to know this because if I say elemental fluorine, you should not just write F, you should write what? F2. Okay. Or when I'm writing an equation, right, I need to write hydrogen element plus oxygen element goes to water. If I want to write that, I need to remember that hydrogen element is H2 and never just H, okay? Plus, what's the oxygen element? O2, okay? So that I may actually balance my equation correctly, okay? So later on, we'll talk about balancing equation as well. So that's why you got to know Hofbrinkel, okay? So what is this? It's the diatomic elements. I don't care if you know P4 or S8. That's just like kind of a cool fact, right? But definitely the diatomic, you guys need to know. Okay, so yeah, that's the periodic table of showing you, which ones are diatomic. And then we got phosphorus, sulfur, and selenium, which are actually polyatomic, right? We got 8 and 4. Yes, go ahead. Yeah, they're always what? That's why it's called di, right? Diatomic. Yep. They'll never be by themselves. They are together. Whereas like iron, that element is by itself, right? Just one a single atom. But those ones are not. Right? Okay. So molecular compounds are usually composed of 2 or more covalently bonded nonmetals. Okay. So water, for example, right? H2O, carbon dioxide, CO2, and then you have like propane, C3H8. Ionic compounds, we actually call them formula units. They're actually not molecules because they're in a crystal lattice, right? And they're comprised of cation, which is plus, attracted to an anion, which is negative, right? And infinitely repeating in the lattice, right? Crystal lattice. So that's just the 2 main sort of bonding motifs that you guys want to just internalize first, right? Of course, bonding gets more complicated, but we'll talk about that later on in the semester, right? So what's the difference? Well, when you have an ionic compound, it's a repeating thing, right? NaCl, sodium chloride, is just the simplest repeating unit of that crystal lattice. So really, we want it to be anal about it, right? Be correct. We need to write this, okay? Because NaCl will never exist as its own thing, okay? And so that's how an ionic compound is different than molecular, right? Molecular compounds, they do exist as their own discrete unit, right? And so that's why that's called a molecule, and that's called a formula unit. All right, so now let's talk about polyatomic ions. It's this sheet that I gave you guys. Okay, and let me show you where you can find it as well. I'll stop sharing here the screen, and well, I'll share my desktop. And then let's go to Canvas, and I'll show you guys where to find a polyatomic sheet. You scroll down on modules, It's right here. Okay, so let's open it up. You guys are looking at it, right? You should learn not just the name of the ion, okay, but also the symbol and the charge. Okay. So for example, the first one that's listed is nitrite. So if I say nitrite, you should write this, NO2 negative, okay? So that tells, so what does that mean? The negative charge is the total charge of this entire molecule. Does that make sense? That's why it's called a polyatomic ion. So unlike Cl minus, this is just one atom with a negative charge, right? Okay, so that's this atom with an extra electron. The only difference here is this whole molecule with an extra electron. Does that make sense? Okay, so the whole NO2 has a negative charge distributed evenly over it. Okay, so that's why it's called polyatomic ions. And then if I write ClO4 minus, you guys should be able to say what? For now, look at your sheet. Perchlorate, exactly. So you really want to know these in that way. Flashcards is the best way to do it, but this is exactly quiz number 2. This is quiz number 2. That's all there is to it. So I'll just like cover one of these up and you fill it in, right? I'll cover one of these, you fill it in. Does that make sense? Yes. Right, so it also has a negative charge? Oh, that doesn't tie together. Oh. Yeah. Okay. Right. Yeah. So it has nothing to do with what are the atoms inside. It's just how many electrons does that whole molecule have extra, right? Oh. So sulfate is 2 minus. That means this whole molecule has how many electrons extra? 2, right? And then there's ammonium. This one's ammonium. And it's a cation, which means it's a whole molecule, but it actually lost one of its electrons collectively. Does that make sense? So it's a collective charge, right? Yeah, collective charge, and that's why it's called polyatomic, okay? So your job is before quiz 2, you guys go on Canvas to figure when that is to memorize all these, okay? That's going to help us with the naming too, right? Okay, so let's go to this slide. Classify each of the following as either atomic element, molecular compound, or ionic compound, guys. So xenon, what do you guys think? Which type of element, atomic or molecular? Atomic, very good. It's just, so xenon, which is be Xe, one atom, right? How about NiCl2? What do you guys say? Look at your periodic table. Don't guess, right? What is NiCl2? Ionic compound, because nickel is a metal, right? And chlorine is a non-metal. What about bromine? Very good. It's part of Hofbrinkel. Diatomic element or molecular element, right? The NO2. Who said it? Molecular compound. Good. So covalent compound, molecular compound. And then E, NaNO3. It's ionic because Na is a metal. And then the rest are non-metal, right? NO3, actually, you should, when you read that, I recognize it as 2 parts because it's ionic. I need to recognize the cation part, that's a sodium plus. And what's the anion part? NO3 minus, which is nitrate, okay? So that's how you should get used to your mind recognizing these polyatomic ions in these compounds. Okay, let's keep going. How about fluorine, guys? Fluorine. Right. B, N2O, molecular compound. C, silver, atomic element. D, K2O, ionic. Good. E, Fe2O3, also ionic, because iron is a metal. Right. Okay. So this is going to be really important that you guys spot what kind of thing it is, because we're now going to naming, and the naming's based on the category. So ionic naming, right, is different than covalent naming for molecular compounds. Okay. So it's a good exercise, right? To just look at the chemical formula and already categorize it. What is it? So that you know how to name it. Okay, that's the whole worksheet that we're doing today. Okay. Yeah, so let's get into that. Naming ionic compounds now. I'm going to go to the board for the rest of the lecture here. So everybody get a piece of paper out. Clean piece of paper. You're going to divide into 4 quadrants. Okay, just do like this. A piece of paper. Okay. And then we're gonna do each quadrant. Okay, so since I don't have a lot of space, I'm gonna erase. I'm gonna do 1 quadrant at a time, but you guys should be able to put it in there, or you can do it on multiple pieces of paper too if you write large. Okay, but it's basically 4 naming rules. So the first quadrant, first left quadrant, is ionic naming. Naming. And first, we need to be able to spot an ionic compound, right? So how do you spot an ionic compound, guys? Metal, non-metal, right? But that's actually not always true. So let's generalize it, right? This is typically, but not always. Always, it's going to be a plus going with a minus. Okay? A plus and a minus. That's really generally how it is. It's typically metal and non-metal, but ammonium chloride, no metal in that. That's still considered an ionic compound, right? So this is how you're gonna name it. First, say metal gets the element name. Okay. And then if it's a monatomic non-metal, what you do is you drop the ending and you add IDE. Okay. Yeah, that looks good. There's a little bit of glare, but I think you guys can see that. Okay, so metal gets the element name, monatomic non-metal. If it's a monatomic metal, remember what does that mean? It's just one atom, right? Non-metal. Drop the ending and add IDE. Okay. So, for example, sodium chloride. Okay, see that? All right. If the metal is a variable charge metal, use Roman numerals to denote the charge. In parentheses. Okay, so IE parentheses 3. Okay, you see? Roman numerals in parentheses. That will denote that's equal to 3 plus. Does that make sense? Okay. Because metals are always cations, right? Okay. So whenever you see that, it means what? 3 plus. Okay. Should we review our Roman numerals? Let's do that. What's 1? What's 2? I. What's 3? I. Okay. What's 4? IV. What's 5? V. What's 6? VI. What's 7? VII. What's 8? VII. And that's all you actually need to know. We don't have anything beyond 8. Okay. So anyways, if you want, if you want to denote that this metal has a 2 plus, then you write 2 in parentheses, right? Roman numeral in parentheses. And then that's just this last rule. If the nonmetal is a polyatomic, use the polyatomic name. So something like sodium nitrate, right? Because nitrate's a polyatomic, right? All right, so you may ask me, Professor, how do I know that a metal is variable charge? What does that mean? Most metals are variable charge. There's a very short list of what we call fixed charge metals. So memorize those, and it's really not a memorization because you guys already know it, okay? Fixed charge metals occur in, what do you guys think? Group? Which metal is it that you can really rely on knowing its charge? Group 1A. Yeah, because group 1 is always going to be what charge? Positive. Also what? Group 2A. 2A, group 2A metals are always going to be what charge? Positive. 2. 2 positive, right? And then aluminum, zinc. Aluminum is 3 plus, but you don't have to memorize that either. Look at where aluminum is. Closest way to the noble gas is where? 3 back, right? So aluminum's 3 plus. Zinc is 2 plus. Why? Look where zinc is. Isn't it in group 2B on your periodic table? Right? Right? Get used to using your periodic table. Group 2B. Cadmium 2 plus, right? Because cadmium is also in group 2B. And then one more, silver plus. Okay, so it's a very short list, as you can see, right? A very short list of what the fixed charge metals are. So when it's a fixed charge metals, you do not need Roman numeral. That's what this rule is saying, right, guys? Okay, so let's practice. Let's do some examples. All right. KBr. Let's name this guy. Let's use our rule. The metal gets the element name. Potassium, right? If it's a monatomic nonmetal, it is, right? You drop the ending. So this was bromine. You drop ene and you add what? Iod. Potassium. What? Okay. Is that clear? All right. Let's do one where we have to use rule 2. FeCl3. What is that? Iron. Right, now you have to figure out the charge of iron. Do you know how you do that? Here's another hint. Use the nonmetal to figure out charge of metal. Okay? Don't forget that the nonmetal, you pretty much always know what its charge is. Either you memorized it from here, or you can figure it out where? From your periodic table. Yep. So where's your nonmetal? Cl, right? What charge is Cl? -1. And how many do you have of those? 3. So that's 3 negative total. Iron has to be 3 positive. They have to be neutral, right, guys? Remember that? Okay. So then what's Roman numeral for 3? Right. And why do I need Roman numerals? Because iron is not in group 1A or 2A or those things, right? You see how easy it is to memorize them, right? So that's why I have to use the Roman numerals. And then what comes here? Good. So you would still use that first rule. It's still the first, right. It's still first rule. It's just combined, right? Yeah. If metal is a variable charge, then you do this one extra thing. Okay? That makes sense? Because there's also this guy. So name that. Name that. FeCl2 is called iron 2 chloride. Okay? Makes sense, right? Right. So that's why you have to use Roman numeral. If I just say iron chloride, you'd be like, which one are you talking about? These are two completely different compounds, right? So if I just say iron chloride, you're like, which one? Is it the iron 2 chloride you're talking about, or is it the iron 3 chloride? Okay. So just do a mental check that it's not a fixed charge metal, right? That's the only time that you don't use parentheses, right? Most other times you will. Okay, let's do it the other way around. What if, let's do one where we use the third rule, okay? So something like, okay, name that one. Very good. Cobalt 2 nitrate. We're using these two rules here, right? If it's a metal that's variable charge, I need Roman numeral because nitrate is 1 negative, right? And I got 2 of them, so cobalt's got to be 2 plus. And then nitrate is the name of NO3 minus, which you have to memorize eventually, right? So cobalt 2 nitrate. Good. Any questions so far? Oh, yes. Let's talk about that. You see how I put parentheses around 1 nitrate and I put subscript 2? Remember, subscripts tell you how many of those things are? So I don't have to do that when it's monatomic because it's not confusing. But look what happens when I leave the parentheses away. Super confusing. Is that NO32? Right? No, I'm trying to say what? NO3, and there are how many of them? 2 of them. So if you break this apart, it's a cobalt 2 plus, 1 NO3 minus, and another NO3 minus. You see? Right? That's what it would look like if you were to meet this thing, right? You'd meet the 2 plus part and then 2 parts of the negative. Does that make sense? And they neutralize out, right? But to write it, that's how you do it, right? Combining this comes that. Does that make sense? Right? Okay. Let's do it the other way around. I want calcium nitride. I want the formula now. I'm going from the name to formula. You want to practice both ways, right? When you're doing this naming. So you want to figure it out. Yeah, you want to make it neutral, right? You know how I do it? Figure out charge on each first. What is calcium's charge? Right, say number first, then sign. 2 positive. Okay. And then what's nitrite? Look on your period table. Where's nitrogen? That's right. Say 3 negative, right? Okay. I just write it on top to keep track, right? Okay. So now I know I need to put this together to be neutral, but I can't put 1 with 1. Would it be neutral? No. So figure it out. How many do I need of each to get to be neutral? That's right. 3 of the calcium, 2 of the nitrites. So Ca3N2. Okay. How does that work? We can double check here. Ca is 2 plus and N is 3 minus. What's 2 plus times 3? 6 plus. What's 3 minus times 2? 6 minus. 6 plus and 6 minus cancel, right? So they have to form neutral compounds, okay? So it has to be Ca3N2. So what you're doing there mathematically is just finding the LCD. What's the LCD? Lowest common denominator, which is 6 between 3 and 2, right? Once you figure out this lowest common denominator, just go 6 divided by 2 is 3. 6 divided by 3 is 2. And that's how you do it, okay? Right. Any questions? Okay, one more. Strontium phosphate. Yeah, remember how we did the other one. Find the charge first, right? What's strontium's charge? 2 plus. What is phosphate's charge? That one you find on here, right? 3 minus, very good. So what would be our formula? What would be our formula? Okay, say it. It's not phosphide, it's phosphate. What is phosphate? Look on your polyatomic. Phosphate is PO4, 3 minus, right? So be careful. Phosphate versus phosphide, right? So that's how you know this is not just a single P, it's a polyatomic. PO4, I need to put in parentheses and then do what? Put a little 2. Okay. So SR3, parentheses, PO4, 2. Does it make sense, guys? Right? Strontium phosphate. Okay, very good. That's it. You just have to practice. That's the rule for ionic. Gonna move to the next quadrant. Next quadrant, covalent naming. How do you spot a covalent compound? No metals, right? No metals, only non-metals. Only non-metals, right? If you look at your chemical formula, it's only non-metals. You got a covalent compound, therefore you got to use these covalent naming rules. Covalent naming rules, thankfully, it's so much easier than ionic. So covalent naming, first element, first atom, gets element name. Second element gets second element, drop the ending, and add IDE. Very similar to that first one, okay? But you have to remember to use prefixes to denote how many of those elements there are. Okay, so use prefixes to denote the number of atoms. So let's practice with our prefixes. Number. So if it's 1, it's going to be mono. 2 is di. 3 is tri. 4 is tetra. And I'm putting the last vowel, last letter in parentheses. I'll explain in a second. 5, penta. 6, hexa. 7, hepta. 8, oct. 9, non. 10. Anybody know 10? Dec. That's right. Deca. Okay. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, right? So a lot of these you probably already know from like geometry class, right? Like pentagon, hexagon, right? Octagon, those kind of things. So that ties to the number. Okay. So now let's do examples. E205. Let's do that. Oh, actually, let me tell you one more rule. The prefix mono is not used for the first element. Okay, so now let's do examples. P2O5. How many phosphorus are there? 2. So prefixes diphosphorus. There we go. How many oxygens are there? Right, pentoxide. And see, now you see why I put the A we're not going to use. Okay, so if the letter following is a vowel, you drop these vowels. So now like 2 vowels next to each other. Pentaoxide. Instead of saying pentaoxide, you just say pentoxide. Okay. So diphosphorus, pentoxide. Good. All right. And what about CO2? What do you say? Right. Carbon dioxide. You guys notice how you didn't say monocarbon? What was this rule? Mono is not used for the first element, right? But it's used for the second element. So what do you call CO? Carbon monoxide. And you can drop that O that follows mono, so it's not carbon monoxide, right? That's why you do that. One more. P4S10, what do we say? Tetraphosphorus. Okay, I heard it. Keep going. What's the ending? Decosulfide, right? The ending is always IDE, right? Okay. Tetraphosphorus decosulfide. Is that clear, everybody? Okay, awesome. All right, that's that for covalent naming. Okay, third quadrant. Let's divide this in half. The third one, the fourth one. So now we're getting into what we call acid naming. And there are two types of acids, binary acid and oxo acid. We're going to do binary acid naming first. Okay. Binary, what does binary mean? Two, right? So binary means two types of atoms. Only. That's what binary means. Okay, two types of atoms only. If you see more, then it's not binary acid. Okay, and then we have to define what an acid is. Acid. First of all, how to spot it? How to spot an acid? When chemists write it, they write it with an H in front. Okay, leads with, and not just H, but it's the proton, the H plus. So have you guys heard of hydrochloric acid, for example? Right, that's HCl. You see how it leads with H? And that clues you in, okay, I have an acid. Why is it binary? It's two types of atoms. One type of atom, the other type of atom. Okay. So what is an acid? An acid is that in water, I'll just write in water, right, over the arrow, it forms a proton. Okay. And that's what makes something acidic. So you guys drank orange juice, you tasted limes, all those things. They're sour because they're acidic. Because of citric acid, spits out a proton when in water. Okay, and that's what makes things acidic. Okay? So we call this a hydrogen that has lost its electron. We call it a proton. We'll learn more about acids later. Okay, but right now, oh hey Sebastian. Right, so that's a proton, right? So that's what an acid is. That's what makes things acidic. Okay, that's why it leads with H. Okay, so HCl. Oh, let's do the rule. I'm gonna use the hydro prefix. And then plus ending. Okay. Um, Actually, it's hydro prefix and the roots plus ic ending. So here's an example. HCl, hydro. Okay. Fluor is your roots. And then ic, acid, is the ending. Okay. Let me color code it so you guys can see. Right, the root of the word, the root of the element, and then ic, acid. Hydro is your prefix, right? Hydrochloric acid. Is this a binary acid? How can you tell? Leads with H, two types of atom. Go ahead and name it. Hydrobromic. Very good. Acid. Oh. Okay. Let's do one more. HI, what's it called? Hydro ionic acid. Nice. Okay, you guys see how that works? Right? With the binary acid naming. Last one. And then that's it for today's lecture. Oxo acid naming. What are oxo acids? How can you spot them? It contains oxygen. And they are derived from your polyatomics. Okay. Notice how an acid is looking very much like an ionic compound. Do you see that? Where the Cl carries the negative charge, like in hydrochloric acid, and the H is actually not an H, it's an H plus. So all acids are actually looking very ionic, okay? So here, the only difference is the anion is polyatomic. And so you add as many protons as necessary to neutralize out the polyatomic. Okay, and then also notice, guys, look at this list. Does everything end in ate or ite? You see that? Everything ends in ate or ite. Okay, so that's going to become our rule. Okay, 8 turns into ic acid, and ite turns into us acid. Really simple. Okay, because it's derived from the polyatomics, right? So everything in 8 and ite. So here are some examples. Let's do H2SO4. Everybody's heard of this one. Find the polyatomic, guys. Which one is it derived from? Which one is it derived from? And name it. Sulfate. Okay. Right. So let's write it. Sulfate. Okay. So we see that it's an 8 ending, right? So it's gonna get turned into sulfuric acid. See that? 8 gets turned into ic. The only thing here that's kind of funny is should not be sulfic acid, okay? Because sulfur is sort of an exception. It keeps the whole thing. It keeps its whole element name, not just the root. And some of them do that, okay? So you just kind of have to get used to it. I know the rules are like changing on you a little bit, okay? But that's how you do that, right? So now if you take H2SO3, what is the polyatomic? For now, you can use your sheet. Sulfite becomes what? Sulfuric acid. You see the difference between sulfuric acid and sulfuric acid? Okay. So ite becomes us. 8 becomes ic, ite becomes us. That's all there is to it. Okay. So even when you're doing something like HiO4, name that. What is the polyatomic? Per iodate. Very good. So it will be what? Per io. Get rid of the 8 and replace it with ic acid. Per iodate becomes periodic acid, right? Okay. Let's do this one. H3PO3. What is the name? Phosphorus acid. Very good. The two ending, right? Yes. This is phosphite. I turns into us. So phosphorus acid. Alrighty. Any questions? All right, so I'm gonna leave these up here. As you guys do the worksheet, okay? That's all you need to know. That also completes the first third of chapter 3's lecture, and I'll upload this by the end of the day. Okay. Any questions? Yes. Oh, right. Thank you. I forgot to mention something. Remember we said you need to add as many H as there are charge. What's the charge of sulfate, everybody? It's for now. You can look at your sheet. That's okay. Don't guess at me. Right, 2 negative. So guess how many protons I need? Proton is what charge? Positive. Okay. So how many H do I need to put in front of SO4? 2. Okay. And it's still an acid. Remember, acids, all acid leads with the proton, right? And so that's why it's H2SO4 not HSO4. So why is it just HIO4? Why is that? Right, because IO4 is just negatively charged. But why is it H3PO3, everybody? Yeah, PO3 is 3 minus. So how many protons do you need to neutralize it out? 3. So that's why it's H3PO3. Okay. Now, if it's not H3PO3, well, there's one called, if you look on the right, you see H2PO4 minus. You see that? Fourth down on the right column. Right. So since phosphate is 3 minus, but right now they only put 2 protons in front of it, it still has a charge, right? So if it's 3 minus and you only put 2 protons in front of it, you have how much left over? A negative. That's why H2PO4 is negatively charged. So that's also something you don't have to memorize extra. Is that PO4 is 3 minus. So if you put 2 hydrogens there, that's plus, then it's H2PO4 is negative. And that's called dihydrogen phosphate. Okay. It actually is technically an acid, but it doesn't have the acid name. You know what I mean? It doesn't have the word acid in its name. But yes, technically it is an acid. Okay. Yeah. All right. Actually, let me show you guys one more thing. How to memorize these. I'm gonna get rid of this rule because I think it's the easiest. You guys have it in your notes, right? And on the video. So don't worry, you got it. You got it on the video. So you have any things that start with hypo, things that end in ite, things that end in ate, and then things that have per and end in ate. Okay. So for example, you have ClO, ClO2, ClO3, ClO4, and they're all negatively charged. Okay, so which one is this called? Hypochlorite. Okay, you see? Then this one more oxygen is just chlorite. One more oxygen is chlorate, and one more oxygen is perchlorate. You guys see that? Okay, that's how the naming goes. So what separates these prefix and the suffix is just one more oxygen, okay? So if you get to the bromine family, it's gonna work the same way. Hypobromite, bromite, bromate, and perbromate. You see that? Okay, same idea. And then we have IO minus, IO2 minus, IO3 minus, IO4 minus. Hypoiodite, iodite, iodate, periodate. Right? Now, do you notice that all negatively charged? Where's chlorine, bromine, and iodine? Everybody, look on your periodic table. Where's chlorine, bromine, and iodine? In what group? Right. And group 7A like to be what charge? -1. See, that's how, right? Helping you guys to memorize these. Okay, so now boom, you got it. 12 of them already under your belt. Okay, 12 of them are under your belt. Okay. Other things that kind of fit this kind of pattern. This is called sulfites, right, everybody? And this one is called sulfates. Sulfate has one more oxygen than sulfites. Okay. And why is it 2 minus? Well, where's sulfur on the periodic table, everybody? Where is it? 6. 6A, yeah. So that's why it's 2 minus. Make sense? All right. This one also works. PO3, 3 minus, PO4, 3 minus. Phosphites, phosphates. Okay. Why is it 3 minus? Where's phosphorus? Where's phosphorus? 5A. That's why it's 3 minus. Right? So it's kind of nice to remember that, right? Okay, so you got a few more under your belt now. The rest of them, you kind of just have to straight up memorize. But there's one more trick I got for you. If you just memorize this column, all the 8s on your sheets, then what can you do is you can use, if I remember what bromate is, I know that 2 oxygens less is hypobromite and 1 oxygen more is perbromate. You see? So then you can just memorize the less, okay? So those are some tricks for you guys, but at the end of the day, you just gotta know those, right? Otherwise, it's gonna be very difficult for you for the rest of the semester. Yes, this is the way we communicate, right? Okay. Any other questions? Did I answer your question? Yeah. Any other questions? Yes. Yeah, so if you just memorize 8, right? You know that per has 1 more oxygen, ite has 1 less oxygen, and hypoite has 2 less oxygens. So let's say I don't even know these, but I know IO3 minus. IO3 minus is called iodate. Then if I see IO4 minus, then I know it's per iodate. And if I see IO2 minus, I know it's got to be iodite. And IO minus is just hypoiodite. You see? Yeah. Because it's always 1 oxygen difference. You see that? Yeah. Like, if you know phosphate, then you know phosphite, right? Any other questions? All right.